very, very beneficial. All right. But another thing I'd like to share with you, is this does not necessarily have to be a linear relationship. This data could also, hopefully you can picture this data forming a parabolic. Coming up with a more parabolic relationship between the data, in which case you would not want to come up with a linear regression linear equation, but more of a parabolic regression of the data. So let's spend the second part of the class. The class going through more of a parabolic, coming up with a parabolic equation. All right? And this parabolic equation will come about in a completely different way. The way you're going to get a parabolic regression equation, let's write that down. Parabolic regression equation, the way we're going to come up with this equation is completely different. The way we're going to come up with this equation is to know how to work with matrices. All right, so we're going to have this rather large 3x3 matrix where we have n representing that element, the summation of x, which we already know, the summation of x squared, we already know that. We're going to put the summation of x here in that position, the summation of x squared in that position, the summation of x cubed, which we have not found yet. Here in this location, we're going to put the summation of x squared, the summation of x cubed, and the summation of x to the fourth power. And that's going to be multiplied by our solution, which the three elements of this matrix would be a to the 0, a to the 1, a to the 2. This is actually our solution, and that is going to be equal, to another matrix where in this position we have the summation of y, the summation of xy, we know that, and then the summation of x squared y. All right. So all of this data is easy to get. All of this, I'm certain that if you're uncomfortable with matrices, you're uncomfortable with math in general, this would seem very, very, very confusing. But it's actually very, very easy if you know how to work with matrices. All right. So this n, we've already told you what that represented. That n represents the number of data points that you have. And again, this data that we're using is coming primarily from 4 unique points. So n for us is 4. All right, so that's 4. The summation of x, we already had that information. The summation of x, we said, was 6. Let's try to put all of this together. The summation of x, we said, was 6. Yeah, there we go. The summation of x, we said, was 6. The summation of x squared, we said was 14. Summation of x squared, we said was 14. All right. The summation of x, we said that was 6. The summation of x squared, we said that was 14. And the summation of x cubed, which we'll put here, we had not figured out yet. Let's do that over here. summation of x cubed, all right, we hadn't figured that out yet because we didn't need it for the linear regression line, the other regression line that we just did. 0 cubed, that's 0. 1, sorry about that. 1 cubed, that's 1. 2 cubed, that's 8. 3 cubed, that's 27. The summation of x cubed, that is 28 plus 8, that is 36. 28 plus 8 is 36. All right, so the summation of x cubed, is 36. We'll put that right here. That's 36. All right, the summation of x squared, that's 14. I'm just really using this as sort of a guide. The summation of x cubed, we just figured that out, 36. And now we need the summation of x to the 4. We hadn't figured that out yet because we didn't need it to come up with a linear regression line. Let's do that right here. Try to squeeze it in. Summation of x to the 4, 0 to the 4, 0 to the 4 is 0. 1 to the 4, that's 1. 2 to the 4th power, that's 16. 3 to the 4th power, that's 81. The summation, try to squeeze it in here, the summation of x to the 4, if we add all that up, we end up with 82 plus 16. Let's just do the calculating right here. 82 plus 16 is 98. That is the summation of x to the 4. And we're going to put that right here. 98. 98. All right. All right. So that matrix, which came from this right here, this part of the equation right here, times your solution, which is represented by A0, A1, and A2, we'll tell you what that represents in a second, is equal to the summation of y. Well, we know what the summation of y is because we did that already. Right here, the summation of y is 450. Summation of y is 450. Right, 450. All right, the summation of x times y, we did that right here. That's 850. That's 850. And then the summation of x squared y, we have not done that. We have not done that yet. But let's do it right now. Let's do it on this form right here. Let's sort of rewrite this. All right. So we got 0, 1, 2, 3. I'm just rewriting the points that I've already given you. We have 0, 100, 150. I'm just rewriting the data that I have up here because I need a little bit more space. 2, 100, and 3, 200. All right, so now what we need is we need x squared. We need x squared y. All right, that's what we need. All right, so 0 squared is 0 times 100. That's just going to be 0. X squared y here, 1 squared times 50, that's 50. Because 1 squared is 1 times 50 is 50. 2 squared, that's 4 times y, that would be 400. Oh, that would be 400. That would be 400. And then 3 squared, that's 9 times that, that would be 1800. 1800. All right? So, now the summation of x squared y would mean adding all of this up. Well, we get 2,200 and plus 50. This all added up is 2,250. All right? So that is what would go right here. The summation of x squared y would be 2,250. What we got right there. All right, so now what you have is a matrix equation where this is the solution. A sub 0, x, but this represents a sub 0, a sub 0, a sub 1, and a sub 2. All right? That is what this represents. All right? And this a sub 1, this a sub 1, a sub 2, and a sub 0, the way we're going to use this is to substitute into this equation y is equal to a sub 0 plus a sub 1 x plus a sub 2 x squared. So once you are able to solve this matrix equation, you would substitute a sub 0 here, a sub 1 here, a sub 2 here, and you would have the parabola that best represents the data that we were working with that we showed you earlier. All right? And it turns out that if you go to all of my shows, I document, I edit them, and I put them on Dominate Math, my Dominate Math YouTube channel. So it turns out that in previous shows, we have solved equations like this, 3 systems of equations, in a variety of different ways, up to 4 different ways. We only have time to solve this problem in one way. We only have time to solve it in one way, okay? So, but if you go and you look at go to YouTube and go to my Dominate Math channel, you look for where it says 3 systems of equations, and you'll see a variety of different ways to solve this 3 systems problem, this matrix equation right here, all right? So let's just solve in a way that we call the Cramer's technique. All right. So the way we're going to solve this equation, is we solve for x separately, and then we solve for y, and then we're going to solve for z. All right. So the way we do that is we find a bunch of determinants. All right, so the determinant that will remain consistent for all of the denominators is the determinant of this matrix right here. So we have 4, 6, 14, 6, 14, 36, 14, 36. That should be a 36. 98. All right? And that would end up being the denominator for all of your answers. 4, 6, 14, 6, 14, 36, and 14, 36, 98. That would represent the denominator for, sorry, you didn't see it. Only thing I did was rewrote the same matrix that I have here, I have down here. And we're going to do the same thing over here. All of the denominators are the same. So you'd have 4, 6, 14, 6, 14, 36, 14, 36, and 98. So you would need to find the determinant. You would need to find the determinant of that matrix. And it would take some time for us to do that. We have videos on YouTube that teach you how to find the determinant of this matrix. All right, so we're not going to spend a lot of time to do that. But you could even, there are ways to putting this in the calculator. And if I had my real good calculator, I'd do that. But I've done this problem before the show started. And it turns out that the determinant of this matrix is 80. The determinant of this matrix is 80. If we had time, we'd show you how we got that 80. But we don't have the time. All right, so that's 80. The determinant is 80. So the denominator of each of these solutions is 80. All right. Now, the way you get the numerator is to take these constants here, and if you're solving for x, you replace these constants for the x column. If you're solving for y, you take these constants and substitute these constants into the y column. And if you're solving for z, you're going to take these constants and substitute into the z column. All right? So let's go about doing that. All right? So, and everything else will remain the same. So we're solving for x here. Let's take these constants and substitute into this column here. So we have 450, we have 850, and we have 2,250. All right, so that's our x column, and let's keep everything else the same. 6, 14, 36, and 14, 36, 98. All right, so you want to find the determinant of that. And again, this would take some time to do. I have videos where I show you in great detail on how to solve the determinant of a 3x3 matrix. This would take some time to do. We don't have time. We only have roughly another 10 minutes in the show, and I don't want to spend all of it just trying to find the determinant of a 3x3 matrix. But you go to my Dominate Math Mathematics channel, and you learn how to find the determinant of a 3x3 matrix. You take your time, and then you'll discover that if you take your time, you will get 7,800. All right, 7,800. All right? All right. So now you divide that out, and what you'd end up with is 97.5. 97.5. This actually represents a sub 0. I said x, but it actually represents, for our problem, a sub 0. All right? So now, typically in a standard Algebra 2 class, this would be an x value, a y value, and a z value. But because of the type of problem that we're doing, we're just going to call this a sub 0, a sub 1, a sub 2. All right, so now let's solve for y, or for our problem, this would be a sub 1. All right, so we're solving for y. So now what we're going to do is we're going to take these constants and substitute them in for 6, 14, 36. All right, but everything else will remain the same. So we'll keep the 4, 6, 14. So we have 4, 6, 14. That remains the same. But now what we're going to do is replace the 6, 14, 36 with this constant column, because we're solving for y, or in this case a sub 1. So we have 450, 850, and 2,250. All right, and now we've exchanged the constants for this column here. Now we're just going to bring this column down, bring down the 14, 36, and 98. We want to find the determinant. I'm sorry. We want to find the determinant of that. I brought down the 14, 36, 98. All right, so you're going to have to put that in the calculator or do it by hand according to the steps that we've already outlined in past videos. All right, so if you do that, you find the determinant of this rather large matrix, you're going to end up with a negative 6,200. All right, and if you divide that out, you're going to get a negative 77.5. All right, that's going to be your A sub 1. That's going to be your A sub 1, negative 77.5. All right, I believe that's negative 77.5. You put that in the calculator. Last but certainly not least, let's solve for Z, or for our problem, we'll call that A sub 2. A sub 2. We're solving for Z. So what we're going to do is substitute these constants into the Z column. We're going to substitute these constants into this column, and everything else here will remain the same. So what we have is we'd have 4, 6, 14, 4, 6, 14. All right, and then we keep this second column the same, 6, 14, 36. And now we'll replace this column with the constants that we have here. We have 450, 850, and 2,250. You'd have to find the determinant of that. And in finding the determinant of that, I've already done it. I've already done this work. I put it in a calculator, and you get 3,000. And you perform that quotient, you get 37.5. And that would be your A sub 2. All right, so now you would take A sub 0, which we said was 97.5, A sub 1, which we said was negative 77.5, and A sub 2, which is 37.5, and you would substitute into this standard form here. And what you'd end up with is y is equal to A sub 0, which is 97.5 plus A sub 1x, that would be minus 77.5x plus A sub 2x squared, that's 37.5x squared. This is equal to y. This is the equation of your parabolic regression. This is the parabolic regression equation. All right? This is your parabolic regression equation. All right? This is the equation that best represents, let's go back to the data that I had plotted here. I had the points 0, I had the points 0, 100, 150, 2, 100, and 3, 200. This data, if I plotted it, I plotted all those points, 0, 100, 150, 2, 100, and 3, 200. All right? If you were to draw the best parabolic representation of this data, it would form the equation of the parabola that I've got right here. All right, so if the data that you have represents more of a parabolic relationship, you would go through this process, come up with this equation, and now you could extrapolate, you could predict or anticipate the amount of money, like I did in the previous equation. You could predict how much money could you have 5 years from now, 10 years from now, assuming more of a parabolic relationship. All right, we're not going to do the examples like we did here with a linear regression, but I'm hopeful that you understand what I am saying. All right, so this is a parabolic regression line right here, and we have a linear regression line right here. All right, so that's about all we have time for.